Okay, hi there. Welcome to our talk. My name is Lukas Heinrich. I'm a particle physicist working at CERN, and I'm going to give this presentation together with Alessandra, who is also connected, who is a senior system administrator at the University of Manchester. And we're both working for a particle physics experiment called Atlas, and we're going to talk about how we use Kubernetes to streamline our infrastructure. And so just to introduce our work a bit. So the main place of our work is CERN. It's the European Lab for Particle Physics Research, and it's located in Geneva, Switzerland. And so here we do many experiments relating to particle nuclear physics, but the main experiment that you might have heard about is the Large Hadron Collider. It's a very big particle accelerator that is 27 kilometer in circumference, and basically it's a big underground tunnel 100 meters underground where we accelerate particles and bring them to collision at 4 interaction points. So we have 2 particle beams, one going clockwise in this big circle and the other one going counterclockwise, and at 4 points that are labeled Alice, CMS, LHCb, and Atlas, we bring those particles to collision. And here we can see what it looks like in the tunnel underground. So this huge magnets that accelerate the particles to almost the speed of light. And so they traverse this 30 kilometer tunnel 10,000 times a second. And at these interaction points, basically what we have done is we have constructed giant cameras that take basically 3-dimensional pictures of these collisions. And these pictures help us understand nature better. So here we basically collide 40 million, we see 40 million collisions per second. And so we generate a huge amount of data. And so just to give you a scale of what these quote-unquote cameras look like. So this is a real-life picture of one of these detectors. So this is the Atlas detector that both Alessandra and I work at. And you can see a human at the center of the image just for scale. So these are some of the biggest scientific experiments that have ever been constructed. And we use that to understand the basic building blocks of matter. So some of the things that we are trying to understand with this Large Hadron Collider is what the basic structure of nature is. So we want to understand how the elementary particles work. So you might have heard about electrons or quarks, but there are a bunch of other elementary particles. And maybe one of the things we would really be excited about is to find new elementary particles, and through that, uncover the nature of dark matter or maybe dark energy, because it turns out that with the current theory of physics, we only understand 5% of the energy content of the universe, and actually 95% of what's out there in the universe is unknown to us. And so one of the other big questions that we're also studying is what exactly the difference between matter and antimatter is, because we see a lot of matter around us, and while we know that antimatter exists, it's not very abundant in the universe, and this is a big mystery that we're trying to answer with this big experiment. And so one of the things you might have heard about the Large Hadron Collider is that we used it to discover the Higgs boson. So this has been a central piece of our physics theory, and it explains what the nature of mass is and why particles have mass. And so in 2012, we analyzed our data, and we could find this new elementary particles. And then Professors Higgs and Angler subsequently were awarded the Nobel Prize because of this discovery that we made here at CERN. And another reason why you might have heard about CERN is because as we're all connected online through the web, this is in part because of that the World Wide Web was developed at CERN. So Tim Berners-Lee, when he was working here in the late 80s or in the early 90s, he developed the web, and it's basically the foundation of what we all use today. And so we need to, we need to record a lot of data to make these types of discoveries. And so it's not surprising that big data and a lot of IT infrastructure has always been very closely linked to the physics that we're trying to do. So not only do we have this magnificent hardware, these huge detectors, but we also have a quite expansive IT infrastructure. And so this is one of the control rooms that we have at CERN. And so just to give you an idea of how much data we're taking, so the big Atlas detector that you've seen earlier in the slide has something around 100 million readout sensors, so that all stream data back to our disk. And so we see 40 million collisions per second, and that gives us a data rate of almost petabytes per second. So obviously we cannot store all of this data to disk, but we do a real-time processing of the data, and then in the end we store to disk something like gigabytes per second, and so this accumulates to order of 10 petabytes per second that all needs to be analyzed in order to give us potentially a discovery like the Higgs boson. And so in order to process all of this data, we are not only relying on the central laboratory at CERN, but we are a worldwide collaboration of physics institutions, so national labs and universities that all pool resources in order to process this data. And so this is what we constructed during the 90s and early 2000s, and we call this the World-wide LHC computing grid. And so Alessandra is one of the leading experts in this area, and she'll basically introduce you how we use that and where we see Kubernetes playing into this.
Yeah, okay, so I'm going to talk about the WLCG computing grid, which was created around 2000, so it is 20 years old. It's a federation of dozens of individual academic institutions, and they provide the resources to global scientific collaborations. The LHC experiments are the primary users, but there are other collaborations using the grid. Participating to the grid, there are 150 sites that actually pledge the resources. They are from big international labs to smaller universities to even department clusters. And at the last count, they offered roughly 1.4 million CPUs for around 10,000 users. Of course, this is a distributed environment, so the challenge is to provide the users with a uniform experience across a heterogeneous computing landscape. And the grid middleware was developed to act as an overlay to provide a common API to all these different resources. Of course, the heterogeneity was also flattened a bit in the past by the experiments and the sites agreeing on what is required for a site to participate to the grid. For example, the main computing resources, the worker node behind the batch system, had all to install a Red Hat family operative system. They needed Intel CPUs and at least 2 GB of RAM per processor. Also, a site in general needed a number of middleware services to be deployed to be recognized as a grid site. The most important one, of course, for this talk is the batch system, but there are a number of other services like storage with the grid protocols for transfers, information system, authorization, monitoring, Squid, software space, etc. This is a quite heavy-duty and rigid deployment model, and of course can be applied only to pledge the resources. But the resources are diversifying and becoming more opportunistic, and we don't have any more control over them and what they deployed. So the WLCG experiments have already started to adapt to this new way of deploying by deploying for example, containers to ease the requirements on the operative system, for example. But this is not the only thing that needs to be done. For how can Kubernetes can help the deployment in this case? Well, for sites, it offers scalable and centralized service deployment. Many of the services mentioned before can be now centrally deployed by someone from the experiments, or someone decided maybe in the region. The UK, for example, has an organization that can do this kind of deployment. This reduces the need to train admins on grid services, which are very, very peculiar to our environment, and can allow to train people instead on something that is more required also around the world. Also, K8 allows horizontal scaling, which allows the services to be scaled and up and down depending on the requirements. Since a site may be diversifying, for example, they might want to deploy resources behind the Jupyter Hub rather than a batch system at a certain point. These can be very helpful. And also, it allows arbitrary size deployment. You can deploy Kubernetes on a laptop or in a large high availability cluster. And this, as we will see in the demo, is quite an interesting feature. As a batch system, it is good at doing resource management. Of course, it has a major missing feature for us, which is fair shares. So right now we are deploying it mostly at dedicated sites. Dedicated means that it is different from pledged. Dedicated means that they run only one experiment. So in particular, since Lukas and I work in Atlas, how does this work out in Atlas? In Atlas, it allows to streamline or to provide a common basis on heterogeneous resources. In particular, on top of the standard batch system sites, we have started to use HPCs and cloud. And our system has a brokering system that calls to this service called the Harvester. Harvester does the submission of the workflows and has an API for each system. When we arrive to K8, this simplifies things, because now we can submit it to a laptop, to a university, or, for example, to Google, and lately also to Amazon. Oh, sorry. You can see here, we started to work on it last year, and there is a steady increase of resources and of sites that are starting to deploy. And you can see that there are all the resources represented. There is CERN, there is University of Victoria, there is University of Chicago, but also Google and Amazon. And in the future, we expect this to increase. There is also Taiwan, incidentally, which was the first one to deploy. How did we achieve this? We have, as I said, this system. The user submits to the broker. The broker creates a central queue depending on what the workflow's requirements are. It talks to the harvester, and the harvester brokers to the appropriate resources. Harvester doesn't submit the workflow directly. It submits something called the pilot. The pilot is a set of scripts that do intelligent things on the worker nodes, stages in the data, runs the payload, stages out the output, monitors the job, monitors the resources. If, for example, the jobs exceeds the memory requirements, it kills it. Also, here it isn't really shown, but in reality the job is run in a singularity container. And what we have done is for Kubernetes is simply to do all this in Kubernetes. Both harvester has been reinstalled as a Kubernetes resource, and it submits to a Kubernetes cluster, and the pilot runs inside the pod. So in the case of Kubernetes, we are also running nesting containers, which is another interesting feature. Mainly is containerd, singularity inside the containerd. Eventually, in the future, the declarative paradigm of Kubernetes may take over. That's at least what we hope, but it is a bit too early. And we will simply transform the pilot features into Kubernetes YAML files, configuration files, job configuration files. So, and with this, I'm passing back to Lukas for introducing the demo.
Okay, yeah, thanks, Alessandra. So in this case, we'll do a little bit of a demo. So if you remember, so that World-wide LHC computing grid, you can basically think of it as a very large federation of clusters. And so traditionally, well, there were standard batch clusters as you would use them in at academic institutions. We, of course, now have Kubernetes that we could use to join this worldwide federation. And so what we will try to do in this demo is to set up infrastructure on a brand new machine to create a Kubernetes cluster and join this worldwide federation. Then we'll also submit a workload into this federation that will then end up on our just deployed infrastructure and do some physics work for us. And so the demo that we prepared is basically simulating high energy physics collisions. And so this is a very important aspect of our physics work. So we need to kind of understand what our data looks like. And so for that, we kind of simulate this using some simulation code. And so with this, I'll just pass on to a demo video that we recorded. And after the video, we'll come back for the Q&A. Okay, so in this demo, we will try to deploy a miniature version of the infrastructure that we are working on deploying more widely on the World-wide LHC computing infrastructure. And so we will deploy two Kubernetes clusters. One cluster that I'll name the job cluster. That's a cluster that actually does the physics work once work is requested. And then another cluster called the harvester, and its role is to monitor the queues of the global LHC user community to see whether or not new workloads are coming in, and it will assign worker jobs dynamically to adjust to the workload, and those worker nodes can then fetch new jobs from the queue as they are coming in. And so at first we will deploy this job cluster. So we will do this using Minikube, and to prepare it properly, we need to deploy also a CERN-specific file system called CVMFS. And we deploy this using a Helm chart this allows us to mount specific persistent volumes into the pods that we will be starting. And so once this file system is installed, we will also provide the cluster with a secret that allows it to communicate to the global LHC job queues. And okay, so this is done, and now we will deploy the second cluster, which is this monitoring cluster called the harvester. And so we will use this time kind to deploy this cluster, and so we will wait a second to get this cluster up and running. And once this cluster is up and running, we will then use Helm again to deploy this harvester service, which monitors the queue, the LHC queues for work. And okay, so here we're using Helm to install the service, and so once the pods are up and running, we're ready to submit some workloads, and we'll just wait a second to get the pods up and running. Okay, there we go. So at the top then, now we use our standard user-facing job submission command line tools to submit a workload into this global queue, and our cluster that we just connected to this global federation will pick up this work and perform this work that we requested for us. And so we get a new job ID, and we will actually go to the LHC global monitoring page to see this new workload that we just submitted. And so we can see that the workload has been registered, and so since now we have a bit more workload on the queue that we submitted to the monitoring service, submitted a bunch of pods in order to satisfy this demand. And so we'll see that one of these containers is now creating, and so once it's creating, we can peek into the container just to see a little bit what is going on inside of this workload. And okay, so now it's up and running, and we'll exec into it, and we'll peek into a few log files as they're coming in. And so here we see that it's now connecting to the global queue, and it's asking for new work. And so we see that it's fetching some new work, and once it's gotten its new work, our workload will start. And so I will just pause here for a second just to show that this workload is requesting its work to be performed in a Docker image, and so we will need to run basically nested containers. So here we see that it's requesting a container image called Atlas/S simulation, and now actually the workload is running in a Singularity container inside of the pod that is running in Kubernetes. And so in order to start this workload, we of course need to first pull the image, and Singularity will do this for us and pull the image from Docker Hub for us. And so we'll just monitor the progress of this software acquisition. And so here we see it's pulling, and those scientific images are usually quite big. So this particular image is, for example, something like 15 gigabytes. So we'll speed up the video a bit just to see that this is pulling correctly. And in the meantime, in the monitoring, our job status has changed from registered to running, just to signal that actually one pod has taken on this workload and is trying to complete it. And so okay, the Docker image is now completely pulled, and now we can see that Singularity is now starting the actual workload. And so this is where the physics start, and so we can see various log files where now we're basically running the simulation job, and the workload in question here is basically a simulation of how particles traverse through this particle detector that we've built. And so it's basically using a virtual version of this detector that we have coded up in order to simulate what our data that we actually record underground is going to look like. And so we can see various physics thing going on. And so now the workload has also finished, and we can go back to pilot, which manages this workload internally in this pod, and see that the resulting data that this workload produces is going to be staged out again to our global storage infrastructure. And okay, so now this is all done, and we can go back to our monitoring to see how our job is being reported there. And so one of the nice things is that this is the actual monitoring page that we use for all our work, and we can look at what host actually executed the job. And so we are checking the host name here of our pod, and we can see that it reported the right host, or reported that the cluster that we just deployed actually took care of this job and completed this workload. And so if we refresh now, the job should also show up as finished. And so we see this, and we can then look at the log files, and here we see basically the same log files that we were just tracing in the pod itself. And so obviously not everybody has access to the clusters, but everybody gets basically these traced logs at the end of the workload. Okay, so this concludes the demo, and it's a very quick version of the infrastructure that we're trying to deploy on the WLCG. Okay, so this was the demo, and so this basically showed us how we can use cloud-native tools like Kubernetes and Helm charts to very quickly deploy resources into this global federation that actually run in production. So we actually connected these Kubernetes clusters that we just created to the global federation and ran a job through all of the production system. I think we're quite excited about this because it shows us what opportunities we can get from cloud-native tools to streamline our processes and manage this worldwide distributed, quite heterogeneous resources that are managed by many different institutions. And so before going to Q&A, we just wanted to acknowledge a few people that actually did the hard work and put together all of these building blocks that we used in this demo. And now we'll go to the Q&A. Okay, hello, can you hear us on the Q&A? So we've received one question, which is from Daniel, who's asking if anybody can run the Helm chart that we used in the demo. So all of the Helm chart and code that we used in the demo is open source. But obviously, so in the demo, we deployed this to production. In order to connect to this worldwide federation, we needed to have secrets in order to connect to this. So it's not like everybody can kind of connect to this without having any proper authentication, but the code that we're developing to construct this federation is open source.
Okay, so I'll answer the other one. Rich is asking how many sites participate in this. At the moment, we have 3 universities, plus we have started to use Google and Amazon. 3 universities plus CERN, of course. CERN is a main player here.
Yeah, maybe to just add to this, so in total, the worldwide LHC computing grid is many more sites, but so we have a handful that are currently deployed in Kubernetes, and we're hoping to expand as we gain more experience with using Kubernetes in these academic contexts. Hopefully, we'll have a larger fraction of these sites run on Kubernetes.
Yeah.
There's another question. So Marcus is asking, do you have specialized nodes, for example, GPU nodes for GPU-related workloads? So the answer is yes. So this is something that we've, especially with the rise of machine learning that we're using in our science, are very interested in. And so there are various institutions that have GPU resources, among others, the Manchester site that Alessandra is working on. And so here, the container paradigm is really fitting well because the software that is used for these machine learning workloads is highly dynamic. And so we are relying, for example, on base images for TensorFlow and PyTorch, or these popular machine learning tools. And so we are also experimenting with integrating those with Kubernetes and, for example, the advanced scheduling that Kubernetes allows us will be helpful here. But so far we've integrated GPUs with the standard batch systems and connected them to the federation, but we use containers, but it's not yet on Kubernetes.
There is a question number 5. Kilian is asking if we have solutions for memory topology heterogeneity. NUMA on the nodes, yes, CERN has that. The other universities don't have it yet. In fact, NUMA is creating some peculiar solutions because you have to pin the resources.
Yeah, the next question is from Michael. So how are the Kubernetes clusters interconnected, or is it more a loose coupling, and can those clusters limit the resources available to the WLCG? And so the answer is, yeah, it's a quite loose coupling. So the nice thing about the workloads that we're mostly interested in is that they're embarrassingly parallel. So every collision that we're analyzing is independent of each other. And so we can embarrassingly parallel distribute this across the world. And so we don't require a very close coupling between the clusters. And so this kind of coordinating service, which we call Harvester, is the one that has all the kubeconfig files and can coordinate and add clusters and remove clusters again. And so it's a quite loose coupling. We are, and also the CERN IT team is experimenting a lot with federated Kubernetes solutions. So we've been looking into Admiralty, or we're also developing our own federation solutions. And we've tried KubeFed V1 and V2. And but a lot of that stuff is not really required for the workload that we need for our science. And so this type of loose coupling has been quite useful. And it's very easy to limit or completely remove a cluster again from this federation by the management infrastructure that we have.
So there is another question. Anders is asking if why we run Docker images within a pod instead of running directly the workload. The reason is that the system that we have in place at the moment is quite complicated. So we run what I call the pilot, which is this set of scripts. And the pilot calls a singularity container rather than a Docker container. And this is working across all 150 sites. And the easiest way for the moment was to simply adapt what we have and run it in a pod, like it was a virtual machine or a bare metal worker node. In the future, we hope to split this and to even split what we call a job, the workload, in smaller pods and use Kubernetes more natively.
Yeah, one technical requirement is that we need to also stage in data and stage out data. And so you see this in other operators like Tecton tasks that, you need to be able to run a sequence of pods, and which goes a little bit beyond of what initialization containers in Kubernetes provide you. But before wrapping up, I did want to answer Per Sander, who's asking whether or not the difference in CPUs between different clusters makes a difference. So in the demo, we were able to submit a workload and schedule it to a specific target cluster. So if this makes a difference in our workload, our brokering will take care of it, but mostly we don't care. And if it takes a little bit longer just because it landed on a CPU that is not as powerful, we usually just deal with it and wait but take the advantage of this global federation instead of focusing on the high-performing CPUs, which might be overcrowded. Okay, so I think we're out of time for the Q&A. Both Alessandra and I will be on the Slack for the next couple of minutes and are happy to answer any additional questions. And okay, thank you very much.